Okay, thank you very much, and thanks for the opportunity to talk to you about the issue of water and potential shortages in a changing world. I should put my sort of expertise cards on the table right from the outset. I'm very much a person who looks at climate change and water resources and the interactions between climate as a driver of water availability and water demand. And what I'm going to talk about today covers a much wider spectrum of issues than that. So I'm going to be drawing very heavily on the work of many other people in the field of water, and unashamedly so. So essentially this is a synthesis of a lot of different ideas that have emerged around water scarcity and population growth over the last, I suppose, 10 or 15 years. And I'm a bit of a messenger, but a messenger with my own ideas that sort of overprint some of that wider, those wider issues. So perhaps we should start by, if I can get that to work, okay, by looking at where we are today. And this graph shows the increase in water withdrawals, so what people are using, have been using historically over the 20th century through to the end of this first decade of the 21st century. And the units here are in thousands of cubic kilometers per year. And at the same time, this growth in population, the measured growth in world population, starting at just over 1 billion people at the start of the 20th century and finishing up close to 7 billion people sometime this year. And as you can see, there's a pretty strong correlation between the total amount of water that's been withdrawn, the top of this graph here, and the increase in population. And in fact, one of the interesting facts, though, is that as this population has increased, the rate at which water has been withdrawn has increased at a faster rate. So there's a kind of an acceleration process or an amplification of the demand for water as a function of population growth. And that's related to a number of different factors that affect, that are related to demography and economics. First of all, they're called the so-called multiplier effects. So as a population grows, and particularly in the 20th century, as the population grows, there are a number of transitions that were occurring. There was economic growth, which meant that we had if you like, a growing middle class that consumes more, and much of what we consume has a water footprint to it. So that increase in consumption multiplies through from the basic increase in numbers of people into increased demand for water. And at the same time, there's been a big demographic shift from rural to urban areas. And people who live in rural areas typically use a lot less water than people living in urban areas. And as one moves to urban areas, more sophisticated sanitation processes actually increase water use as well. So everywhere in the UK, we use a lot of very nice clean water to flush away our waste. That typically doesn't happen as much in rural areas. And so there's another multiplier there, an urbanization multiplier as well. Then at the same time, there's industrial output that's increased through the 20th century. And again, that's feeding the consumer demand for products. And those products have a water footprint as well. And finally, something that's often ignored is the fact that as population grows and as we urbanize and become more centralized, there's actually a lot of wastage that goes on as well. So there's not only is there water wastage in the way that we deliver and store water. For instance, this little blue bar at the top here is water that's actually lost via evaporation from reservoirs where we store water to supply these urban conurbations and irrigated agriculture. But at the same time, there's leakage through the pipework that we use to deliver water, and there's a lot of wastage in embedded water, particularly in food. So 30% of all the food that's produced is never consumed. So we're wasting 30% of the water that's embedded in that food just by producing food that's never actually used. So there's a lot of wastage in the system as well, which is partly a function of the way that society has modernized, and a lack of sort of almost a surplus of available resources for the more well-off parts of society. So if we look at that graph, essentially, if we try to project forward in time, then we might say that if we have this correlation, strong relationship between population growth and water demand progressing into the future, then clearly there is a link between water use and population growth in the future. There's one little feature here that's quite interesting to look at in this graph before we move on, and this is the last few decades of the 20th century going into the first decade of the 21st century. And we seem to see that sort of that multiplier factor dying away a little bit there. So in the second half of the 20th century through to the 80s and 90s, this rate of increase of water was much faster than the rate of increase in population. And now we see that curve diverging again. And this, I think, is partly because most of the population growth is now happening in developing countries. A lot of the population growth in the 40s, 50s, and 60s was in more economically advanced part of the world, where people could afford to essentially use water in a more profligate manner, and the urban areas that people were moving into were more connected in terms of water availability. This growing population that we have now in many developing countries are essentially disconnected from the water system in many cases, because the infrastructure and the institutions are not there to provide the kind of water demands that a growing and economically developing population would be expected to if one was looking at the model of the 20th century. So there's a question now whether this linkage or this multiplying effect between population growth and water is going to carry on into the future. And that's a lot to do with the political economy and institutions around water, rather than the basic underlying factors that I mentioned earlier. Okay, so that's where we are today, if you like. I thought I'd also just sort of give a few definitions of what people think of as water scarcity. I guess the most basic definition of water scarcity would be when the demand for water by a society exceeds its potential availability. And this, by other people, has been termed what first-order water scarcity. So where the absolute amount of water that's available is insufficient to supply the demand. Now, if you read through the literature, you'll find probably as many metrics as there are metrics describing water scarcity as there are researchers working on water scarcity. And what they all show is a similar pattern, but with some sort of with differences, subtle differences between the patterns. Here's one example of a measure of water scarcity. This measure of water scarcity essentially takes the ratio between the actual withdrawals, so what is being used in terms of water, to the raw water availability, how much water there actually is available in a particular area. And this index is applied at a river catchment scale. So each of these little colors is an individual river catchment. So for example, down here we have the Murray-Darling catchment in Australia. And then you can categorize a river catchment by how stressed it is or how scarce water is as a function of this balance between demand and supply. And generally considered threshold for water stress or water scarcity is around a demand being about 40% of the available water, because water is required for other functions as well. And 40% is normally the easily available fraction of the total water supply. So this is the current situation in terms of water scarcity or water stress, according to this index. A spread of river basins around the world with very high stress, where over 80% of the water that's available is actually withdrawn. Another bunch of catchments that are under high stress, and then a whole bunch under medium stress. And you can see that those high stress catchments are located in two main zones across the low to mid latitudes of the northern hemisphere and equivalent latitudes in the southern hemisphere, essentially around the dry subtropics and Mediterranean climates of the world. So in one sense, water scarcity is driven by the raw water availability. These are the dry areas of the world, if you like, or the relatively dry areas of the world. And the other, it's driven obviously by population, how many people are demanding water. And so where you have high population or low water availability, or a combination of the two, you end up with water stress or potential water scarcity. Now, in the real world, what actually counts in terms of water stress or water scarcity is the access to reliable water supply. So you may be in a river catchment that has a lot of water flowing through it, but if you can't access that water, then as an individual or a city or a farmer, you're going to be experiencing a water scarcity situation. And this is often termed second-order water scarcity. So there's enough actual water around as a natural resource, but there are various reasons, either infrastructure or institutional or political, or maybe even water quality issues, that means that water that's potentially available can't be used. And this is essentially what real-world water scarcity is around. It's around that mix of absolute availability and then how much of that absolute availability is actually available for use by society. Okay, so with that background, I want to move on now to look to the future a little bit. And first of all, look at population growth as an acknowledged driver of potential water demand. And then follow up on that by then looking at how that feeds through into demand for water in the future. So here's a set of pretty standard global population scenarios. These come from the UN, showing historic population, global population from 1900 through to the present, 2100, and then various scenarios of how that population might change in the future. And as you can see, depending on the particular underlying sort of principles of that scenario, we can have quite a wide range of possible future population levels, certainly at the end of this century, anything from something extreme like 28 billion, which I don't think anybody believes, but that's essentially assuming fertility remains the same as it is today, through to a peak at around the middle of the century and then slowly declining, which is the population scenario that a lot of people use today. A recognition that with successful economic development, population growth rates tend to decline. So this peak and decline growth rate is very dependent on developing countries actually developing economically in a way that the levels of poverty decrease to the extent that you get this fertility reduction that's associated with improved economic livelihoods. So we have a range of possibilities, and if we just sort of think out to probably the middle of the century, which is where we can be reasonably confident about what might happen, we've got a range from about 8 billion people to somewhere just over 10 billion people that we might be dealing with. So 3 billion extra people, anywhere between 1 and 3 billion extra people in the future. Now, that's a global picture. What gets much more interesting is when one starts to look at what happens regionally with these population scenarios. So this divides that middle of the range scenario into different regions. And as you can see, there are two areas where population growth is projected to increase very sharply right through at least to the middle of the century. And in the case of Africa, here through to the end of the century. So the two regions of population growth are Africa and Asia. Everywhere else, we're in a pretty stable or declining situation. So if we're thinking about population as a driver of water, as ignoring other factors, then the areas we need to be concerned about are Africa and Asia. Those are the areas where, if you like, the population growth hotspots. Then the other factor that that's really important is then the demographic changes that are going to happen with those population growths. So here we've divided, this graph divides population growth just between developed and developing countries. And what you see in developing countries is this crossover. This is rural population, and this is urban population. Somewhere around about 2020, the proportion of people in developing countries living in urban areas is going to exceed the number of people living in rural environments. And that essentially has important implications for water, both water demand and water supply systems in the developing world. Because we're going to have people essentially concentrated in small pockets of urban areas across a wider geographical domain. And so we're going to have to be transferring water to supply the water needs of these people into increasingly concentrated locations across Africa and Asia. So that changes the challenge of supply from being one that's much more distributed if you have a rurally based society into one that's very concentrated with an urban-based society. There are also other issues around water supply in urban areas in many developing countries that relating to the difficulties in providing reliable supplies of water and sanitation, but I haven't got time to go into those in a lot of detail. So if we just look at this, this is a picture of Africa today in terms of where the population is concentrated. And we're already seeing this shift, this urban-rural shift in Africa. But if we go forward through to, hopefully, through to 2035, then you can see how that most of the additional population growth is concentrated in these rural areas. The whole of the west coast, the coastal region of West Africa is essentially going to develop into a connected megacity all the way from Ghana and Gabon through to Nigeria. So we're going to have these very large urban conurbations that present particular challenges in terms of water delivery. So what does that population then mean in terms of water requirements? That's what I want to talk about next. Well, I think the first thing we need to do is think about, well, what would happen if we continue using water in the way that it's been used historically. And this is what often is termed a business as usual scenario. So just carrying on the way we are, assuming that the same linkages between population growth, economic growth, urban versus rural divide produce the same sorts of responses we've seen in terms of water demand that we experienced in the last century. And this is the picture you get under one business as usual scenarios. Embedded in there are all sorts of assumptions, but all of the business as usual scenarios produce a picture that looks like this. You can argue about 10% here or there, but the overall picture is very similar. And essentially what you see is that we get increases in demand across all regions, but very large increases in demand in certain areas. So sub-Saharan Africa, for instance, where we have large population growth and actually quite low relative water use at the moment. Water demand's increasing by over 200% over the present day if we follow a business as usual scenario. China and India are obviously, with their population projections and economic projections, similarly stressed. But even in parts of Europe and North America, those business as usual scenarios show quite a large increase over over the present day use. So that's sort of, if you like, the business as usual. So what does that mean in terms of water scarcity? If we take figures like that and apply those water scarcity metrics that I showed earlier. Well, here's one example. So taking a business as usual scenario, slightly different from the previous one because this is a different study, but this shows essentially where you get increasing pressure in terms of the ratio of demand to available water, where you get decreasing pressure, and where you get very small changes. And everywhere that's black is where there's an increasing pressure. So the ratio of demand to availability decreases. Everywhere that's dark grey is not much change, and everywhere that's light is a decrease. And as you can see, most of the globe, most land areas where people live experience either an increase in pressure or no real change. And that's not surprising because of the underlying population scenarios. More people, more water demand under a business as usual scenario. But these sorts of diagrams can actually be quite misleading because this paints actually quite a sort of a scary picture, if you like, because most of the well, at least half the world is black in the sense of increasing water stress or water pressure. But that's only telling you the change from the present day. And the critical thing is to understand a change from what? So what's the current situation, and how does the increased demand change the stress situation compared to today? And this is essentially the same data, but now showing where we get a change in the stress situation from moderate to severe stress. So everywhere that's grey are areas that were under severe stress today, and everywhere that's black are new river catchments that switch into the severe stress zone or state in the future. And here you can see that there are only a few hotspots where these river catchments enter a high stress situation. And they're scattered around the world. Probably the ones of most concern are the Ganges Basin and some of the Chinese basins, and maybe the Zambezi, I guess, or no, Limpopo Basin. So when we're talking about population as a driver of water stress, we really have to be careful about the baseline that we're talking about. It's very easy to say, well, stress is going to increase, but it's all relative to the amount of water that's available. Right. What I want to do next is move over to talking about possible solutions to this supply-demand gap. And there are essentially three ways one can go about solving this problem of increased water demand with population growth. The first is the traditional route, which is simply to increase supply. So there's a shortage of water. One follows the traditional route. You try and store more water, or you create more water through desalination. You manage the supply side situation. Now, one of the issues with the supply side situation is that these are generally quite what's capital-intensive solutions. This shows for India the relative cost of supply side or measures to augment supply. And there's a whole lot of different examples here, ranging from sort of wastewater reuse through to some quite large projects and desalination. And the marginal cost of bringing in these supply-side solutions is actually quite large compared to this line here, which is the current cost of supply in India. So most of the supply-side solutions are actually expensive, and in some instances where there isn't available water may actually not be feasible either, unless one goes for a desalinization option. The second way to meet this supply-demand gap is to increase efficiency in the way water is used today. There are many examples about the way we can do this. One example is just to change, for instance, the way that we grow the same crop. So here we've got the same crop being grown, but irrigated in a very different way. Flood irrigation on the left, which has a very high water demand, and drip irrigation on the right, which is very, very water efficient. We can, in terms of agriculture, we can increase efficiency through increasing the yield gap. So improved land management. For the same amount of water that you input into the system, you get a greater yield. So you need to actually use less land to get the same agricultural output. You can increase efficiency in domestic and industrial water use as well. So many industrial processes, particularly lubrication, for instance, use a lot of water. If you go to dry lubrication, various other approaches to these industrial processes, then you end up with improved efficiency. Perhaps the more radical solution to meeting this supply-demand gap is actually to change the way that water is used. So it's a little bit analogous to the situation we have with fossil fuel emissions. So the solution to the fossil fuel energy issue is to switch to different fuel sources. So we switch from fossil fuels to renewable energy. That's a bit difficult, that's a bit more complicated in the water situation because there's no real substitute for water. But there are substitutes for the way we use water. So one example might be that instead of everybody eating rice, which has a very large water footprint, at the bottom here, so 1,700 liters to produce 1 unit of rice, one switches to less water-intensive crops. So we're not becoming more efficient in the way we produce the same crop, but we're actually shifting the types of crops that we produce and those to crops that are less water-intensive. The same arguments go for the use of animal foodstuffs, which have a very high water footprint. We can switch from animal food products to non-animal food products and have a very different water footprint. We can also change the way we use water domestically. So we can switch from, for instance, from flushing loos to composting loos. We can actually change the way that we treat our waste and just take water out of it, out of the situation altogether. Now, these aren't always appropriate solutions, but they are solutions that should be considered. And there's no reason why one can't have composting toilets, apart from the fact that partly there are many cultural reasons why people are used to using water to treat their personal waste. It doesn't have to be the case. There are many other examples of substitutions in the way that water is made, water is used, that can essentially take water use out of that supply-demand gap. Okay, so what we've got is a business-as-usual situation and then various possible ways of solving the gap that we have between supply and demand if we follow a business-as-usual situation. And here's just one example of that for the whole of Southern Asia, showing 3 different scenarios of total water withdrawals based on, first of all, the business-as-usual scenario, where population growth takes us up to something like a need of 160 cubic kilometers per year in 2025, and 2 alternative scenarios, one which is very technologically oriented, so basically increasing efficiency in terms of the technologies that we use, and the other that's actually more culturally oriented in the way that people value and use water in their personal lives and the goods that they buy. So changing patterns of consumption, changing the way that water is used personally. And those differences or departures from that business-as-usual situation actually make a huge difference to that supply-demand gap. It doesn't necessarily solve it completely in the case of Asia, of Southern Asia, which is one of those hotspots of population growth. But it's approximately 2/3 of the gap is solved on those, if you like, demand side efficiency and behavioral rather than supply side solutions. Okay, so I want to now just sort of propose a concept which I've stolen from the people working in climate change, because the big catchphrase in climate change now is something called climate compatible development, which essentially means making development plans and planning for development in a way that means that you aren't caught out by climate change and variability. So you essentially, you make your development climate smart. Some people call it climate proofing. I think that's probably the wrong term. But we can think of water in a similar manner, in the sense of thinking about water compatible development. So the two big hotspots for water growth are Africa and Asia, the two big areas where we expect economic development over the future, or where we need economic development if we're going to solve the chronic poverty problems that exist there. And this is quite a nice quote that I sort of bastardized, because I couldn't find the original quote in the end when I was making this presentation. But in a lot of planning around economic development and everything that goes with it, the options that one uses, there's always the assumption that when you build a factory somewhere, or you put in some industrialized agriculture, or you plan an urban area, that there's going to be, the water that's available is going to be there. And that's not just a developing country situation. We just need to look at the Thames Gateway development in the UK, where John Prescott decided that he was going to build however many houses it was, 400,000 houses, in the most water-stressed part of the UK, in the Thames Valley, right at the bottom end of the Thames system. So a decision about local economic development in the UK, but made without any real consideration of whether the water that would be required for that development would actually be available. And so what we need to be doing in terms of thinking about how we deal with the needs of a growing population, and that essentially means development in the broader sense of the word, is that in a way development planning should be informed by water availability, not that we should be expecting water availability to follow development planning. And to do that requires good information and decision support tools to enable that planning to actually take water issues into consideration in an integrated manner. And that's not always the case. Those data and information and the methods of using that information in planning and decision-making processes isn't always there, and is a need from both research and a practical applied point of view. So I want to give one example of an analysis framework that provides both the information and an approach to making decisions. Now, this is something called a cost curve, developed by McKinsey in a number of different applications, and it's quite a complicated graph to show, but essentially it shows two things. This is an example for South Africa. It's showing the total future water requirements for South Africa based on a particular scenario about water demand. And this axis along here shows the gap between current availability and future demand. So there's a 3,000 cubic meter demand gap, million cubic meter demand gap for South Africa's water requirements in 2030. And then all of these little blocks here represents one potential solution to part of that water requirement. So for instance, if we take this yellow block here, it's basically saying that if we go for non-till rain-fed agriculture in the areas where that's appropriate, then we can make up this much in terms along that axis of that water demand supply gap. The y-axis shows the cost of that particular option. Okay? And everything that's negative is actually something that has a positive investment return. So by investing, even though it costs money to invest in that particular option, it produces an economic return that outweighs the investment requirements. And these options are ranked in terms of their net cost. So from something that produces a net economic benefit through to these options on the right that provide that actually cost and have increasing cost to fill a particular sort of pocket of water in this demand-supply gap. So what this does, it essentially lays out all the different options that are available, tries to come up with a good estimate of what the cost is in this case, and then ranks them. And it wouldn't be surprising to know that all of these ones on the left that have a negative cost are generally the demand-side options. So it's the same situation as if you're talking about electricity efficiency. Switching from incandescent to fluorescent light bulbs is a small investment for actually quite a big return in the energy savings that you make and the economic benefits, the cost savings in terms of your energy bills. It's the same for water. All of those efficiency changes and changes in the way that you use water produce economic returns because water is an expensive commodity. It costs a lot to deliver that water. As you go to more of the supply side type options, they require big capital investments. And there's a long payoff on those investments, and they're often economically more expensive. So what you can do then is think of other costs associated with these options. This graph simply shows the economic costs. You can also rank them in terms of other factors, so social acceptability. This axis here could be how socially acceptable different things are, how difficult they are to implement, how long they take to implement, how complicated it is delivering that particular option. So do you need 16 different government departments to deliver a particular option, or is it just one municipality that has to make a decision? Those are things that a decision maker may want to take into account when trying to decide which portfolio of options they actually go for to start narrowing that supply-demand gap. Because there's a mixture of economic and political and institutional considerations that one needs to weigh up in deciding what one uses. Okay, so that's just one example of the way that good information, and not all of this information on here is necessarily good, but if it was good, and a sensible analysis framework, and there are other analysis frameworks that one could use, can actually enable sensible decision making. And you can apply this sort of approach at anything from a national scale, where you're looking at your total national water budget, and you can start allocating where water is used in different parts of the country, depending on your priorities, right down to a catchment scale or a city scale. So at different scales, this approach can be used. But the important thing is that it integrates all the different options into one set of decision choices. Okay, one thing I haven't talked about yet is climate change. And I think we have to deal with climate change because it is potentially an important issue. Or at least we have to assess how important climate change is in terms of water futures relative to other factors. This is one example of the relative influences or importance of climate change versus these other population and socioeconomic drivers of water stress. And what these maps are showing is essentially the change in water stress, so how water stress is increasing or decreasing as a function of both population and climate change, and population in isolation and climate change in isolation. So we can actually separate out the relative importance of these different factors. Everywhere that's with this particular index, everywhere that's orange is actually an increase in scarcity. So it's a decrease in the availability of water. So if we just take this first case here, this is population change only. It's a middle-of-the-road population scenario. So one of the ones that sort of goes through the middle of the set of scenarios that I showed earlier. And the pattern that we see in terms of river basins with an increase in stress is very similar to what I showed earlier. Much of Africa, South America, Australia, South Asia, and the Midwest of the United States is population growth produces an increase in stress. If we then look at this next column, this shows the effects of climate change if the population stayed at today's levels. Okay, so it's climate change alone. And this is for a relatively low climate change, a global warming of somewhere around about 1.5 degrees, a middle range one, somewhere around 3 degrees, and quite a large climate change, about 4.5 degrees global warming. So different degrees of climate change. And if you can compare that to the graph on the left here, you'll see that the big factor driving changes in scarcity in most instances is actually the socioeconomic drivers rather than climate change. Climate change acts as almost like a layer, overrides socioeconomic factors as a primary driver and modulates that societal signal. And what it does is in areas where climate change reduces the raw water availability, it exacerbates stress. And in areas where climate change increases water availability, parts of the world where rainfall is projected to increase, it offsets that socioeconomic water stress. So it acts to modulate rather than actually drive climate change. So that's summarized here by looking at just essentially the number of river basins that are affected by climate change as you go through different parts of the world. What this is showing is the proportion of river basins on each continent that show a significant climate change impact in terms of water stress. That's the blue column. So, for instance, in Africa, about 30% of river basins are significantly affected by climate change. The rest of them, there's no signal, or the situation is improved. And this brown graph shows the fraction of river basins that are already stressed. So it's essentially how many of those river basins that are negatively affected by climate change are already in a stressed situation. And in most instances, it's roughly between 1/2 and 2/3 of those river basins that are affected by climate change are currently stressed. So climate change is adding to an already stressed situation. In other instances, so in Africa, for instance, one of these basins that is affected by climate change but isn't already stressed would be the Congo Basin. It's essentially an underutilized basin. River flows are probably going to decrease slightly, but it's just not an issue because under any population scenario, the Congo River Basin as an aggregate doesn't become stressed. Okay, so let's finish off then. I don't know if I can answer the question whether water scarcity in the future is a fact or fiction, but there's certain facts that we can probably state that influence whether water scarcity is going to be a problem. I think it's a fact that population is going to increase, and mostly in the developing world. So if we're thinking of population as a driver of water stress, then those hotspots are going to be in the developing world. I think it's a fact that if we continue to use water as we have in the past, and I guess one could say use and abuse water as we have in the past, then many people in the developing world are going to experience water insecurity, which one can think of as the flip side of water scarcity. But I think it's also a fact that in many cases there are affordable solutions to many or to a large proportion of these future water requirements. So business as usual, yep, there's probably a problem. But if we're inventive and take some of these less conventional approaches to narrowing that supply-demand gap, then we can deal with a large fraction of that supposed emerging water scarcity. I think the other key thing to bear in mind, which I haven't talked about in a lot of detail, is that even with the technical, behavioral, and raw water supply factors that control absolute first-order water scarcity, in many cases, water scarcity is about politics and economics and governance. It's about those second-order issues around access to water, access to clean water, that are part of the political economic system through which the raw water availability is, if you like, filtered to get to the people who need it. In extreme cases, and in the majority of the cases, there are expensive solutions to water shortage. So a lot of the water shortage that people talk about is actually water that's easily available. For a large proportion of the world's population actually lives in the coastal zone. So if you're prepared to pay for it, we've got essentially an infinite supply of water in the oceans. We just have to take the salt out of it. So in really high-stress situations, there are, in fact, technical solutions that can supply the water, but we have to be prepared to pay the cost. And one of the dangers is that because the surface water, the easily available water, is often cheaper than the expensive water, society tends to over-abstract from the easily available water, because it's the cheap option, with all the environmental and social consequences that come from that over-abstraction. Climate change is important, but it's often not the most important factor. It's one of those factors that essentially drives and affects the raw water availability, the total amount of water available, and to some extent the demand for water. But it's a modulating factor rather than a driving factor in most instances. I think it's clearly a fact that without good information, accurate information, or accurate information with some representation of the inaccuracies around it, the correct decision tools, and an approach to development planning that is water compatible, we're going to repeat the mistakes of the past. So it requires both a change in the way we think about water, but also the political and institutional enabling environment to enable these new paradigms about water use to actually emerge and mature and take over from the paradigm of the 20th century. So water scarcity, I know those of you who like novels, there's this genre called faction, which is sort of, you take some facts and then you weave a story around it. And I think in terms of water scarcity, we're in a similar situation. There are some very strong facts that we know about. And society is actually weaving a story around those facts as we go into this century. So whether it becomes a horror story or a love story or a success story depends on the way that society actually writes the story. So we are dealing with a potentially water scarce situation, but I think society in many instances has the solutions available. It's just a question of actually society getting its act together to make those solutions happen. Thanks very much.
Well, thank you very much, Mark, and good afternoon to all of you. Mark, some time ago, asked me to act as a respondent to his presentation, and I'm very grateful for him for giving me that opportunity. Now, I wasn't entirely sure what the content of the presentation would be like in detail, and with such a broad, ambitious presentation like that, it's quite difficult to to pull out particular issues because there are just so many questions and important things which arise from something like that. So I cheated a little bit and I've preempted it and prepared a couple of slides of essentially 4 points that I thought probably would come up in Mark's presentation, and perhaps that if they didn't come up, then I thought I wanted to bring your attention to them because I feel that they are quite important in terms of our whole interpretation of the significance of water scarcity in the future for society and for water management. Okay, so quite quickly then, the first point I wanted to raise was this idea about our confidence in the projections out into the future of water availability, water scarcity, and many of the other factors which are important when it comes to contextualizing the significance of water scarcity. So how reliable are these projections? And then a second question is just to think a little bit about, well, actually how useful, how important are these projections in terms of the reality of decision making about water resources? Now, when it comes to making projections, we have pretty good confidence in our ability to be able to characterize the spatial and temporal dynamics of physical water availability in the current. We also have quite good confidence over the next 2 or 3 decades to project that out into the future. Now, as Mark has already said, climate change is going to start to influence the physical availability of water. So moving out beyond 2 or 3 decades becomes quite difficult, and we have fairly high levels of uncertainty, particularly because we don't know for sure what's going to happen to precipitation, as to what the detail of water availability will be like. But that's the physical availability. But when it comes to trying to understand the context of the socio-economic, political and institutional context within which water availability will be important to understand, then the uncertainties become very large. And as we saw, it depends on the assumptions we make about population growth, about per capita demand for water, and so on. So to illustrate that point, I've gone back to some work done quite a while ago now by Peter Glick and published in 2000. And Peter Glick produced a summary of the published literature which was projecting future water demand or water withdrawals out. And these are based on projections made during the 1970s and the 1980s as to what water demand would look like. And he then also plots the projections here, and this is the actual water use. And the point that comes out from that curve is that many of the projections tend to quite strongly overestimate demand for water and water withdrawals in the future. But also, interestingly, the further back in time those projections were made, the greater the overestimate about demand. So I think we need to be very cautious about what we infer from some of the projections that we see, particularly projections which go a long way out into the future. We can also ask the question, well, what is the value of knowing what some of these indicators might be like in 40 or 50 years' time? And I think the importance of that question is very relevant in terms of the context of looking at climate change, where as a community, where we've been looking at water resources, water availability as a response to climate change, we've tended to look out to the 2070s, 2080s, 2090s to look at what's the long-term impact of climate change on physical distribution and availability of water. Now, that information is very useful in terms of the international negotiations around climate change and for painting a picture about what we want to avoid in terms of the negative impacts of climate change a long way out into the future. But those projections don't really provide much usable information or have much traction to policymakers who are interested in water resource management decisions which need information about the current situation and what's happening over the next 10 or 20 years. So we need to be thinking very carefully about what is the purpose of some of the projections that we're producing, particularly in terms of climate change. The second point that I want to make is this issue of scale and the amount of detail that is provided within some of the projections of water availability, water scarcity, and so on, because there are some problematic issues there. Now, there is a very large degree of aggregation in much of the work which is done on water availability. The aggregation occurs in terms of the spatial scale, so we often look at indicators which are representative of water availability, per capita availability at a national or even sometimes regional or global scale, and we miss out on a lot of detail. And we also compress many of the complexities about water supply and demand and smooth them out by taking quite simplistic indicators such as per capita water availability. And the reality of water management is in the richness of things like the cost curves that Mark was showing, the detail at the village level, the river catchment level, or perhaps the transboundary river basin level, and that's where we need to be thinking about how we can approach a more effective management of supply and demand around water. So to think very carefully about the indicators that we're using and the level of detail and how relevant those indicators are for making decisions about water resources planning is a key point. That brings me to the third point, which is one that I want to make, which is about really trying to integrate our analysis of water availability and water scarcity and set it in the context of other uses of water. And particularly here, I'm interested in the agricultural use of water, and I think that's come out quite nicely through Mark's presentation, just the significance in terms of the volume of water which goes is allocated for agricultural production, for irrigation, so that for many parts of the world where irrigation is a key part of food production, we have to be taking into consideration the agricultural sector alongside the water sector. And to illustrate that point, I've got quite a complex slide here which comes out of some work that I've been involved in China, and I'll just talk you through this slide because I think it makes a nice point about the importance of water vis-à-vis climate change in the future. So what we have here is the results of a study which was done at the national level to look at future food production in China, staple food crops, wheat, rice and maize, and the current production is about 400 million tonnes per year. And we've simulated using crop models and a hydrological model for China the future food production under conditions of climate change, but also a whole range of other socioeconomic changes. And along the x-axis here we have the different combinations of drivers of change. The left-hand one here is looking at what are the effects of just climate change on total crop production. This one is climate change plus carbon dioxide fertilisation effect. And the third one here, which I'll concentrate on in a second, is climate change constraint and food production constrained by water availability as it's affected by climate change. On the y-axis, we have the percent change in total crop yield for different points in the future. Okay? And each set of bars represents results for the period of the 2020s and the 2050s with different emissions rates of greenhouse gases. So the first cluster of bars then represents percent change in national food production for 2020 and 2050, only under climate change conditions. So we're just looking at changes in rainfall and changes in temperature. And what we see from that is that actually the effects of climate change are quite modest at a national level of aggregation. And even by the 2050s, we're only looking at 2 or 3% decrease in crop yields. If we factor the biophysical effects of carbon dioxide fertilisation into the crop modelling process, we get a beneficial effect in all our scenarios in the future, quite significant beneficial effect. Interestingly though, when we couple water availability and the response of water availability to climate change, but also water availability which is constrained by growing demand from other sectors, so industrial sector and the domestic or urban sector in China, what we find is that water availability in the future becomes a significant constraint to the ability to grow crops in China and to physically irrigate the current level of irrigation. So the point that I want to make here is that when we look at some of these future scenarios, and particularly when we look at climate change, then it's very important for us to cut across different sectors, particularly the agriculture sector and the water sector. And that slide takes me quite nicely to my final slide, final point, which Mark didn't talk about very much, so it's quite nice to end on a slightly different note. Now, the work that we've been doing in China shows us that if we make some assumptions, fairly reasonable assumptions about modifications in agricultural technology, about improvements in water use efficiency, in irrigation and so on, that broadly within China we can meet national targets for total food production and per capita food production and per capita water availability. But in order to do that, to implement those technological changes, to keep up with population growth, to keep up with growing demand for water, we have to make assumptions about quite high energy intensive practices and responses in terms of adaptation. And that's led us to think more carefully and to recognise what we would argue as something which has been under-recognised, and this is that the water sector itself is very energy intensive. So many uses of water require a lot of energy. And when we think about adapting to some of the challenges that Mark has profiled and that we think about in terms of climate change, then many of our solutions involve additional energy requirements which are going to exacerbate the problems of climate change. So thinking about the water energy nexus is critical, and by that nexus we can think of water use to create energy through hydropower, etc., but also energy use for supplying, treating water, and so on. So there are processes of abstraction and conveyance, treatment and distribution, end use of water, heating in the home, for example, wastewater treatment. Many of these processes are highly energy intensive, and these are the sorts of responses which are on the table when we think about how we're going to respond to climate change, how we're going to respond to some of the other socioeconomic drivers of change in the future. Just to give you two examples of this, is that in India the emissions of greenhouse gases are about 95 million tonnes of CO2 equivalent, which is about 6% of national emissions, just for abstraction of groundwater, primarily for agriculture. And work we're doing at the moment in China is coming up with an estimate which is about 0.5% of China's total emissions, which is simply from abstraction of groundwater for irrigation. And therefore, in many of our responses to these challenges that we face in the future, because a lot of the responses are energy intensive, we're going to increasingly need to factor into the decision-making process the energy requirements to support those policy responses. Thank you.